Hi, everybody, and welcome to the Engineering Tomorrow Water Treatment Lab. My name is Eric Einset. I am actually was trained as a chemical engineer. I got my bachelor's at Cornell and then went to the University of Minnesota for a PhD. And I worked for about 30 years. I've been working for about 30 years, 17 with GE. And when I was at GE, I actually worked in the water business, where we worked for a company called GE Water, where we treated and serviced water systems for industrial customers. And then the last 14 years, I've been working at Global Infrastructure Partners, and we work and invest in various infrastructure businesses, including water treatment businesses or water businesses. So what I like to do is take you through the water treatment lab, and I hope you'll have some fun doing this. I'll give you a feel for how water is processed. We are used to just turning on the tap in your house and clean water comes out. Not everywhere in the world can that happen, and there's a lot of engineering that goes into making that actually happen. The lab was developed, as you may know, our labs are all developed by engineers and delivered by engineers. This one was developed by Edgar Martinez, who was a civil engineer, you'll see. And then we also have engineering college students that help us out, and Mona and Caroline helped on this one. So first question is, do you know what your water footprint is? Now, you may have heard of your carbon footprint, which is what is it that you do? Where do you travel? What is it you use that creates CO2? But what about your water footprint? And a lot of people don't think about this because you use water for drinking and for cooking. You use water in your toilet for showers and for baths. That's the obvious stuff. But it turns out your water footprint is a lot bigger than that, because a lot of the products that you use water, and a lot of them use a lot of water. You may think about, other than water, other than drinking, what did you use your water for today? And also, how many times have you used water? So your water footprint, as I kind of alluded to, is defined as the volume of fresh water you use to produce the goods and services you consume. And that's along with the direct water that you're using. Now, it's important is that it's fresh water, because there's a lot of water in the world. Most of the world is made up of ocean water, as you can see from this graphic. And trouble is, ocean water only has very few applications. What we use as human beings is fresh water, and usually in most manufacturing processes that use water, they also need to have fresh water. You can see the fresh water is a small percentage, 3%, and out of that 3%, a lot of it is unavailable to us. A lot of it is locked in glaciers, a lot of it is underground. And even less than 1% of the 3% is in rivers and lakes, which is easy to get to. Now, obviously, there's also this underground water. It can be in aquifers, and quite often aquifers are the source of our drinking water. But again, that's not all accessible. So what does it tell you about the importance of water? Don't know what it tells you about the importance, but water is important, as I think you know. Water is critical for our well-being and for life. So let's just ask a couple of questions here. So that, we'll give you a feel for where water is used. So first of all, how do we measure water? We measure water in terms of volume, gallons or liters, cups. So how many cups are in a gallon of water? Don't know if you know this, but it's 16. So 16 cups gets you to a gallon of water. So how many cups are in a liter of water? Now think about a liter is about a quarter of a gallon. So you might guess, do a quick math and figure out that that's about 4. Turns out to be about 4.22 cups. Now, what about that Dunkin' Donuts coffee, or actually latte, that you see a picture of there? How much water do you think it takes to make that latte? Now, you might think of it as just a volume of milk and coffee and water, but there's a lot more to it. There's water used in processing the coffee beans. There's water used in making the styrofoam cup. There's water used in transporting these products around the world. There's water used in for cows to make the milk for the latte. So it turns out that the actual water footprint of that latte is huge. It's 190 liters, which you may not think about, but that all has to be fresh water. It has to be water that a cow can drink. It has to be water that can be used in the industrial process, on top of just the water that you make your coffee in. So it's just useful to think about everywhere that water is used, and as water becomes more scarce, and it's becoming scarce in various parts of the world, a lot of parts of the world are struggling with access to enough water. So we'll show you a video that talks a little bit about the importance of water, and also how water is being wasted. So after watching the video, just try to grab a couple things. What are 3 things that you learned in this video that you didn't know before about water? And what are some ways that you can reduce your water footprint? Just a little hint, for example, on some of the 3 things you learned. One of them, think about capturing some information about how much water is lost and wasted. That's one. And also think about, or try to grab a fact about how we use water that's very, very clean for something that's not very clean. So let's go ahead and start that video. So now that you've seen the video, what are some of the surprising things? One of the things that amazes me is how much water is lost in our pipes. I think you saw some numbers from London and from the United States. Just leakage of water is a huge amount of loss. And that is something that just fixing those leaks can mean that there's a lot more water available for people. And the other one I think I wanted to point out was, our toilets in our houses. When you flush your toilet, the water that goes into that toilet is just as clean as the water coming out of your sink to drink. And you really don't need that quality of water to use it for sewage. So again, another place where you could save in the processing of water, but there are lots of reasons why that's not commonly done now, because you have to keep clean water and not so clean water separated in your house. And then the last thing that I think came up in this was water causes a lot of heartache, a lot of death from diseases in many parts of the world, and a lot of conflicts. So water is a very important thing, and it's only going to become more and more critical that we have engineers finding ways to solve these problems. So let's talk about what's in water that makes it contaminated. Roughly you can divide it into three different areas. One is suspended solids. So that's like you can see in that cup. It was a cup of clean water, but there's a bunch of dirt and gunk and things floating around in it, and it looks really gray and ugly. And you probably wouldn't want to drink that just because you don't know what's in there. Now, those suspended solids, the good thing is they don't dissolve in the water, so you can see them. And you can actually filter them out, and you can also agglomerate them and settle them out. And that's what you're going to be doing in your lab. You're going to be filtering these suspended solids out. So that's one class of material that contaminates water. Another class of materials are what we would call dissolved solids or dissolved materials. And that can be probably the most common or the one that you'll know the easiest is salt. So the ocean has a lot of dissolved salts in it. That's why if you get ocean water in your mouth, it tastes really salty and disgusting. That's a little harder. Those are already all in the water, and they're on a molecular or atomic level, and you can't just filter those out. You need to remove them through some chemical process quite often. One is called softening or ion exchange. Sometimes you can remove them through a membrane process, which is a reverse osmosis process. Sometimes you can remove these materials, which can include gases. You can remove them just by aeration or de-aeration. So basically getting the gases to release. Like for example, in your soda bottle, there's carbon dioxide in that. That's what gives it bubbles. And when you open up that bottle, you hear psst, and that's the beginning of the release of those gases from that water. So that's another type of material that contaminates water. And then the last one, or general class, is the one where people get sick from. And water is key to life. And as a result, there's a lot of life living in water. So that's where you got your bacterias and your algae and your funguses and your viruses and protozoa. And if you're taking biology, you've probably recognized all this. Basically, the way you approach removing them essentially is by killing these bacteria, so that if you do ingest them, they don't grow in your body and make you sick. So the way that's done is usually through chlorination, putting chlorine ions in water. That'll rip these things apart and make them benign. Or you can also do it through ultraviolet radiation, radiating the water. That can also kill these microorganisms. So in general, you want to have multiple process steps where you take you remove each of these in different types of process steps. And that's how water treatment works. It's typically not a single step. It's a multi-step process, which is very much what chemical engineers learn, and is very much a part of chemical processing. Water treatment is a multi-step process. So as an example, I'm going to show you a video here of a multi-step process that they use in Singapore, where they take water and collect it from various sources, including sewage water. And they process this water with a number of different steps. And essentially, as it says on the slide, first you collect rainwater, used water, reservoir water. You add chemicals so that all these suspended solids start to coagulate. So they basically kind of start sticking together. So the small particles become bigger particles. And these bigger particles are called floc. And because they're big and kind of a little bit more mass, they start to settle in a process called settling in a settling tank. And then that creates sludge. And then there's clean water up top. Then that clarified clean water gets filtered through sand filters, multimedia filters, different types of membranes maybe, and gets cleaned even more. And at that point, they've removed the dissolved solids. It's okay to have some dissolved solids. It's not a bad thing. And people, there's minerals in your water. They're not going to harm you. And then finally, the water goes through a disinfection process where they use chlorine and ozone, for example. And then they store this clean water. So that's the multi-step process. And this video will take you through it, what I just described. This was an example of the multi-step process used in Singapore for treating the water for their city. It turns out that every multi-step process for water treatment is going to be a little bit different. And it's really going to depend on what contaminants are in your water and so where your water came from. So what's interesting about this technology and the engineering of cleaning water is that it always varies. So when I was in the water business, when we were looking to do work with an industrial customer to develop a water treatment process, for example, or even to treat, say, a cooling tower water, we had to first take a sample of the water and understand what was the source. So what is it that we have to deal with, and what is it that we need to remove? So therefore, that was step one, and then from that, you decide on how to design the process. So that's why, because this is very bespoke to where you live and where the source water is coming from, we need engineers who have the technical skills, that know the equipment and the chemistry, and know how to manage basically any source of water. So let's get to what you're going to be doing today. You're going to be working on one step in the multi-step process, and that's the filtration step. And you're going to be designing and building and then testing out a water filter. And it's going to be a multimedia water filter. So let's talk about how that's going to work. So you've heard, I'm sure, of the engineering design process. Engineering is an iterative process. You'll use your basic skills in math and science and chemistry and biology and physics. And you'll get concepts, you'll put together a trial, you'll try it out, and you always have to kind of try it again because you'll see things that don't work quite right. So it's a constantly iterative process. And we say it's good to fail. I mean, you're expected to fail, and it's not really failing because every time you go through the process, you're learning something else about how things work. And it's not a question of failing, it's a question of learning and then applying that as you continue to evolve your design. So some of the things that have been developed related to water is, you can see on the page, the life straw, which is again a filtration process or a filtration piece of equipment. I think there's probably a limit to how good water you can use this with. And then these ceramic water filters just gives you an idea of another design process. And inspired. And it says inspired by nature. I mean, quite often we look at how nature naturally treats water. I mean, the water cycle on Earth is naturally a cleaning process, and it's a great motivation and a guide to how we can then try to replicate that. This lab is going to focus on the filtration process. So what is water filtration? Again, it's the process of removing or reducing contaminants that are not dissolved in the water. So they're suspended solids. And what you're going to do is you're going to actually be using a variety of materials, filter materials, to try to design something. So what industries use process of water filtration? Pretty much every industry that uses water and has to have a water treatment plant so that they don't actually get it directly from their municipal source. But almost every process has some sort of filtration process. So this is quite fundamental. So I've mentioned a multimedia filter a couple of times. So basically a multimedia filter is exactly what it says. It's media is the material that you put in your filter. So it's the sand, it's the gravel, it's the stuff that you're going to have your water flow through, and it's going to capture those suspended solids. So a multimedia means that you have many different types of media. So this is an example of a multimedia piece of equipment. You can see there's two tanks here on the left-hand side where you have water flowing in and the clean water is coming out. Obviously, you capture your contaminants in the media. So every once in a while, you have to stop the process, backwash it, actually have water flow back the other way. And then you can see there's a back flush valve there. That cleans the media out, and then you can start using it again. So that's a multimedia process. You're going to be making something that looks a little bit like what's on the right here, but we're going to show you how we're going to set that up. So this is a better picture of what you're going to do. What we've done is we've provided you with a variety of media. So you should have some gravel, some sand. There should be some coffee filters, cotton balls. You can use napkins or paper towels. Maybe you can find other things. And what you're going to do is you're going to start with a plastic bottle, which you should have. What you're going to do is you're going to cut it in half. So cut it in half. And now you have the bottom of your experiment. And then you're going to turn the top upside down, and you're going to build your multimedia filter in this top piece. So you can have layers of your materials in the top piece. One of the challenges you're going to have is how do you make sure not everything falls right through your cap of your bottle. You have to have some kind of a seal there or some way to hold it in place. You need to think about, what should I put in first? Should I put the finest material first, the coarsest material first? Let's think about if you wanted to capture first the coarse stuff and then the fine stuff later, so you don't clog up your filter. And that's going to be your filtration system. So here's a few hints to how you want to think about it. You should try to build multiple. First of all, put thought into how you're going to design your filter, and then what is going to be, as I mentioned, the order of the materials. One thing I should mention before we even get to the filter is you need dirty water. So we're not going to just have you find dirty water, because that's not a good thing. You're going to make some dirty water. So you're going to have a second bottle, and you're going to take regular tap water, and then we're going to have you add pepper, ground pepper, which is kind of a coarse material, and you're going to also add a little bit of cinnamon. Now the ground pepper is kind of coarse. The cinnamon is very, very fine. So you're not going to be able to clean it all up, but at least the water will smell good because it'll smell like cinnamon. Now, what you should do also is after you've designed and built your filter, you should first run some just clean water through it just to saturate it. And basically also that can test how fast does the water flow through. And then when you're ready, dump out the clean water in the bottom part, and then pour your dirty water in and see how effective your filter is at cleaning up the water. And be sure to take some pictures so that you can compare. Now, what is it that we're going to be looking for? Well, before we show you what we're going to look for, here's a little video that is an example of somebody actually doing the filtration experiment. So you can take a look at that. All right, so you've seen from the video, give you a feel for how you can build your filter and some of the decisions about what materials to put in, what order to put them in. So let's talk about what are you actually measuring? Now, the best thing you can measure just without some extra sophisticated equipment is pretty much the color of your water. So what that is a representation of is what's called turbidity. And turbidity is kind of like the transparency of the water. So how clear does it look? Does it look clean and clear? Does it look dirty and murky and mucky? Now, to measure turbidity is actually a bit of a more sophisticated, they have sophisticated tools to measure that. The way they work is that you take a little bit of your sample of your water, put it in a very clean vial, you put it in a machine, and then that machine will shoot a light through it, or a laser light, I think it's laser, and it'll measure the intensity coming out. And then it'll actually calculate a more accurate turbidity number. But for your case here, for your experiment, we can just use this scale. It's good enough. So I think originally you should have a nice and murky bit of dirty, cinnamony, peppery water, which should hopefully be up in the hundreds range. And you should compare that to the clean water that comes out in your sample collection to see how much of that turbidity came down and how clean your water looks after you filtered it. So again, this is just, now that the units of turbidity are called NTU. If you'd like to know what that stands for, I would recommend you Google it and search it up. It's a complicated word, but again, that is a very well-defined measure of turbidity, and it's only valid when you use one of these sophisticated instruments that's actually measuring it. Now, why is turbidity important? Think about it this way: you're developing one step in a multi-step process. So the first step, early step, is your filtration. If you don't get a pretty clean or make a good stab at your initial clarification or filtration of your sample, then you're going to need to do more process steps, maybe another filtration or multiple filtrations after that. And that just costs more and more money. So what you want to do is have a pretty good filtration step that you're designing. But filtration and cleanliness is not the only thing. You also want to have a pretty good flow rate through your filter. So it's a combination of flow rate and cleanliness or turbidity that's going to be a measure of the quality of your engineering design. So just to put some numbers on the engineering design and the cost of it, we've given you just some kind of arbitrary numbers. So if you have not cleaned your water at all, basically virtually no filtration, then you're going to have a cost penalty, and we're going to call that cost penalty $100. If you can bring your filtration, your filtered water down to, say, under 100, then the cost penalty is lower. So what you're trying to do is optimize your system so that you reduce your cost penalty. But that in itself isn't the only thing. You also want to try to produce a lot of water, as I mentioned. So what you should do when you do your filtration is also measure how much water flows through your filter in 60 seconds and compare that with your colleagues, with your friends in your class to see, can you get something that has a good flow rate, but also a low turbidity and a low cost penalty. So that's basically the breakout. I hope you have fun with it. It's usually quite popular. If you really enjoy this, we do have an extension to this lab, which is more about settling and the settling step of a water treatment process. But also, if you're also interested, you can learn more by exploring things like osmosis, reverse osmosis, fluid dynamics, Stokes' law, flow in porous media, clarifiers, and things like that. And as we said here, there's various engineering topics that are related to this. So I leave you with that, and you should go off and try your design and see what you can do as far as making an effective water treatment. So have some fun with that and enjoy. All right, so hi everybody again. My name is Eric Einset. Hopefully you've already completed the water treatment lab, the filtration element of the water treatment lab, and I hope you had some fun and were able to build an effective water filter. This is an extension of the lab, so if you want to take this to the next level, we're going to now add another process step, which is called settling. And what we're going to do is have you do a settling step, and then that step will feed into the filtration step. So now you're going to build a two-step water treatment process. You're going to use the same dirty water, the water that had the pepper and the cinnamon in it. But in this case, you're going to build a kind of a rudimentary settling tank. So let's see what this all means. Now, just to review, this is just a different picture of an example of a multi-step water treatment process. So if you start with dirty water, we'll call it brown water, which is quite often what it's called in the industry. Quite often the first step that the water will go through is called settling, which is what I mentioned in the other lab, where you add a chemical to the water so that the particles start to coagulate, flocculate. You create floc, and then you let that floc settle to the bottom of the tank, and then you take it away, and all the clean water is on top. So that removes large suspended solids. And the basis for that, if you're going to design that from an engineering view, the basis for that settling rate is called Stokes' law. And we'll talk about Stokes' law in just a minute, but you can see what the formula looks like right there. What'll then come out is, after that, you'll typically go into a filtration step. It could be a multimedia filter. It could be what I'm here on the page. There's microfiltration, ultrafiltration. From there, quite often you'll go to a reverse osmosis. And by the way, this is for generating very clean water. And then from there, you might go to a disinfection step, and then now you have clean water. So just to give you a better feel for this settling step, a clarifier is a very large industrial scale tank for letting the water, the coagulants and the flocs settle. And the picture at the top right is an example of that clarifier. So if you've ever driven near a water treatment facility, there's a very good chance that you'll see something that looks a little bit like this, a very large circular tank. And they'll have a paddle that kind of slowly rotates. and gets the flock to form and then settle out. So let's talk about, once you've got flock in your water, how fast does it settle? Because you need to know that in order to design how long the water should sit in that tank. And that's determined by something called Stokes' law. And Stokes' law is just the formula as you can see. So the V is the settling velocity. The particle diameter is d, and that goes to the square. And really what you're trying to do by coagulating small particles into larger ones is to make that particle size d big, because the bigger that gets, the faster it'll settle out, and especially to the square number. The other factors are not that variable, honestly. G is the gravitational constant, that's constant. The densities, rho sub p and rho sub s, are basically densities of the coagulant and density of water. Obviously, density of water is relatively stable. And then the eta, or that's a nu, I guess, on the bottom, another Greek letter, that's another factor called the dynamic viscosity. And again, it's a variable that doesn't really change. So the biggest variable you have to play with here is that d, the diameter of the particle that you create. So if you go through and you could just plug in these numbers into this formula, and we have a couple of questions there. So if you have a particle that's 10 microns in size, and you can see how many that is in meters, you should be able to calculate how far it'll settle in 5 minutes. And then if you make that particle 5 times bigger, how far will it settle in 5 minutes? So I'll let you do the math on that, and I'm sure you can work it. So what you're going to do now is we're going to make a simple clarifier. So we're going to start again with a bottle, just like the one we had before. So this is going to be your clarifier process. What you should do, again, is cut the bottle in half. But in this case, instead of making a filter like that, you're going to take the bottom half of the bottle, and you're going to punch some holes in it. And those holes, they should be all on the top, on one side of the circumference. I don't know if you can see it. You may not be able to see it. You can maybe see it there. I've got the picture where you can see the 3 circles. I used the scissors to punch some holes in the bottom of this. You might do better if you could make the holes a little bit smaller. So maybe use something that's sharp, but you can get through that, but don't hurt yourself. And then what you're going to do is you're going to take that settling tank, which is basically what this is, and you're going to put it inside the top half of the bottle. So I can put it in like this. And now what you've got is a little settling tank. You keep the holes at the top, and that's kind of going to be something that's called like a weir. So basically the water will sit in there until it gets high enough, and then it'll start flowing through those holes over the top. And what you can do then is put your settling piece of equipment here kind of at an angle. And if you slowly pour your dirty water into here, you're going to see that the water will mostly stay on the bottom. You're going to start to have some settling, probably of pepper. And then as you start to let it go higher and higher, slowly, don't pour it in too fast, the cleaner water will flow over the top over your weir and into the bottom part of this. And you can see that in the picture there. It's a little hard to tell that the water here is a little bit dirtier than the water here, but it has made one step. It has removed some of the materials. And then at that point, this water can now be put into your filter. So now you have a multi-step process where you first have a settling step, and then you have a filtration step. So that gives you a sense of kind of an extension of the lab to make it more interesting. So then a couple of things to consider. Can you build a structure? Can you build a stand so that you can hold your clarifier up and then it'll automatically flow into the multimedia filter? How does the speed at which you pour this in impact the effectiveness of your settling tank? Does it matter how many holes or what a pattern of holes that you use as your weir in your settling tank? Could you mix your water with something that makes it more effective at settling, a coagulant? That could be tough. I don't have an answer to that. There are a lot of coagulants that they use in industry, but I'm not so sure. They're not things that you typically find around the house. And can you think of other ways of designing a process, a piece of equipment that slows the water down so that things can settle out, and then finally, lets the clean top layer of the water flow further? So just to think about this, if you think about how a stream or in nature works, you have water flowing down, and there'll be places where there are slow spots in the stream because of the shape of the stream, or there could be eddies or rocks that'll slow it down. And it's around those slow spots that you start to get silt depositing. And that's exactly the same process that we're talking about here. By slowing down the water as it flows, you give it time to settle out the heavy stuff. And then the cleaner water continues on. So that should be it. So that's a little bit of an extension activity that you can do to the original water filtration lab to make a multi-step process. So I hope you've enjoyed the water lab. It's very much a topic of importance in the world today. It's very much a place where chemical engineering and environmental engineers, and also mechanical engineers building equipment for pumping and everything, and also civil engineers, because large civil works are involved in building water treatment plants. All kinds of engineering that goes into providing clean water for you. So when you turn your tap on, you can have a drink. So thanks for listening, and good luck.